Welcome to Lecture 7.2, where we're looking at linear programming, specifically using a graphical model. Linear programming is one of the most remarkable and useful mathematical techniques developed in the last 65 years. It is used to deal with a variety of issues faced by businesses, financial planners, medical personnel, sports leagues, and others. Typical applications include maximizing company profits by adjusting production schedules, minimizing shipping costs by locating warehouses efficiently, and maximizing pension income by choosing the best mix of financial products. So linear programming is very common. It's used a lot in business, as you can see, in all types of business. And it's a great technique to learn to try to figure out how to optimize a system. Okay, as it says here, to either maximize something like your profits or productivity, or minimize something like costs, etc. Many real-world problems involve inequalities. For example, a factory may have no more than 200 workers on a shift. Okay, so if I can have no more than, be careful with this. This says that the number of workers I have is less than or equal to. Okay, sometimes when we see these words more, we think of the word greater, but no more than is actually less than or equal to, right? If I can have no more than 200 workers on a shift, that means the number of workers I have is less than or equal to 200. So be careful when you're translating word problems. And must manufacture at least 300 units, okay? At least is actually a greater than or equal to, right? I have to manufacture at least 3,000 units, so I have to manufacture 3,000 or more, or greater than or equal to 3,000. Again, the word least tends to make us intuitively think of less than, but at least means greater than or equal to. At a cost of no more than $35 each. Again, less than or equal to $35. How many workers should it have per shift in order to produce the required number of units at a minimal cost? Linear programming is a method for finding the optimal, which is the best possible solution for such problems, if there is one. So let's first remind ourselves, how do we graph a line or linear equation? Okay, so we have an equation, for example, 3x minus 2y equals 6. And what we want to do is find 2 or 3 points. 3 points is best because you can, if you calculate 1 point wrong, there will always be a straight line between 2 points. But if you calculate 3 points and you don't have a straight line, you have through like a triangle, then you know you've done something wrong. So 3 points, by graphing 3 points, you actually build in a check that you've done the work right. So what we do here is we pick a value for y and then plug that value. So here we picked x equals 0. We plug that back into our equation and solve for y. So if we plug x equals 0, we get negative 2y equals 6, or y equals negative 3. We can do this the opposite way, is to pick a value for y and then solve for x. So here we've picked y equals 0. We plug in 0 for y and we get 3x equals 6, and so x equals 2. So it doesn't really matter if we pick an x value and plug it in and calculate y, or pick a y value and calculate x. Once we have the 3 points, then we simply plot it on a graph and basically connect the dots, okay? So let's see how we graph a linear inequality, okay? Here we have example 1, graph the inequality 3x minus 2y is less than or equal to 6. And that's what an inequality is, right? Greater than, less than, greater than or equal to, and in this case, less than or equal to 6. The first thing we're going to do when we're graphing any linear inequality is to replace the inequality, in this case less than or equal to, with an equal sign, and then simply graph the line. Well, we've already done that in the first, in our review there. However, it's important that when you're doing inequalities, if the inequality is less than or equal to, you use a dashed line to graph the line. If the inequality is greater than or equal to, or less than or equal to, then we can use a solid line. Okay? In this case, it's less than or equal to 6, so we're going to go ahead and use a solid line. And we saw this in the last example, when we were reminding ourselves how to graph a line. Okay? Now what we do after we've graphed the line with a dash or a solid line is we pick any point that is not on the line and plug it into the original equation. So we can see this line here. We can find any point that's not on the line, for example, the origin. And the origin is really one of the best points to pick, because then it means x is 0 and y is 0. And so it makes our calculation really easy to figure out if it's part of the solution or not. Use the origin 0, 0 if possible. Plug it into the original inequality. 3 times 0 minus 2 times 0 is less than or equal to 6. Well, that's 0 is less than or equal to 6, which is true. If when you plug it in, you get true, then you're going to shade the side with the point. So the origin is here. When we plug it in, we see it's true, so we're going to shade everything above and to the left of the line here. So everywhere you see my dancing pointer, because the origin is there, we're going to shade everything on that side of the line. Let's pick a point on the opposite side so we can see what happens when we do that. Okay, so if I pick a point on the other side, let's, for example, if I pick 3, 0 right here, okay, well 3 times 3 is 9 minus 2 times 0, it's 9 minus 0 is 9, and then we'd have 9 is less than or equal to 6. That is not true, it's false. And so if we had picked that point originally, again, axis lines are good because that makes one variable 0, we would shade everything opposite it. We do not have to pick 2 points. We just pick one point that's not on the line, and if it's true, as in the case of the origin, we shade that side of the line. If it's false, in the case of 3, 0, we shade everything on the opposite side of the line, which you can see is true for either side here. Okay? So again, we're graphing inequalities. Replace the inequality with an equal sign and graph the line using a dashed line for less than or greater than, and a solid line for less than or equal to or greater than or equal to. Once we've graphed the line, then we look at a point that's not on the line. Doesn't matter what side, just one point that's not on the line. Use the origin if possible. And if we plug it into the original inequality and get a true statement, then we shade that side of the line. If we plug in the point that's on and we get a false statement, we shade the opposite side. Okay, because that means that in this case 3, 0 is not part of the solution, so it's everything on the opposite side. So try another one here. Go ahead and pause this and see if you can graph x plus 4y is less than 4. Once you've done this problem, go ahead and hit play and then see if you got it right. So the first thing we're going to do is graph x plus 4y equals 4. We're going to find some points. Here I just found the x and y intercept. Kind of cheated a little bit as I didn't do a third point. And since it's less than 4, not less than or equal to, we're going to use a dotted line. Then we're going to pick a test point that's not on the line. Unfortunately, here my graph isn't there. I wish I'd put it up there earlier. 0, 0 is not on the line. And you would actually see the graph there, of course, with your line on it. And we can see that 0 is less than 4, so this is true, so we would shade the side with the origin. Okay, there's my dotted line. Because it's less than, we picked the origin was true, so we shade everything on the side with the origin. Linear inequalities can be very simple, but they can be confusing sometimes to students when they are horizontal and vertical lines. Remember, a horizontal line is y equals something. Here we have y equals 2, this line, but our inequality is y is greater than or equal to 2. So we have a solid line, and then we shade everything above it. Vertical lines are x equals a constant. This line is x equals -1. but we want x is less than or equal to -1. So again, we have a solid line here, not a dashed line, and then we create shade everything to the left of -1 because all of these values are less than or equal to -1. So horizontal and vertical lines are some of the easiest to graph, but if you don't practice it, it can be confusing, like what do I actually do there? Sometimes students get a little bit wigged out when there's only one variable. Hey, where's the y? How do I know what y is? Okay, well, it doesn't really matter because x is 1, -1 all the time, or less than that. So sometimes we have a inequality system, just like we had a linear system, a system of linear equations. We can have a system of linear inequalities as well. And so now we're trying to figure out where these intersect. If you remember before, when we had linear equations, we would look at the point where they were intersecting. And so we're really doing that again, but now we're looking at where the regions, the shaded regions that include all the values, intersect. The first thing we're going to do is to graph both of these lines. 3x plus y equals 12, and, and x equals 2y. And we get these two lines. We get negative... Wait, let me see which one is which. Negative 3x is here, plus 12, and then y equals x over 2. They've just divided this, so it's a y equals, okay? You can leave it as x equals 2y, as this line here that's going up, okay? Since they're both less than or equal to, we use solid lines for both. Now we have to figure out which part of this. Notice that these two lines dissect the graph into 4 different regions. So in this case, what we can do is we can pick a point in each of the 4 regions, okay? Because we have 4 different parts of the graph: the blue, a white section here, a white section here, and a white section here, okay? So if we pick 6, 0, we're in this first section here. We plug those values in and we see that now we have to answer this for both equations, right? So we plug it into the first one, we get false. We plug it into the second one, we get false. As soon as I get a false, I don't need to plug it into the other equation, okay? What I'm looking for here is a true, true. So as soon as I hit a false, I can move on to the next quadrant. Another point is 0, 4. So I'm 0, 4. I'm actually in the blue section here. When I plug it into the first equation, I get 4 is less than or equal to 12, which is true, because 3 times 0 plus 4, okay? When I plug it into the second one, 0 is less than or equal to 8. That is true as well. Now I don't have to go any further, so I know that 0, 4, which is right here where you see my dot, is part of the solution. So I'm going to shade everything in that section of these two linear inequalities. But just to kind of demonstrate, here I have 0, -2, which is below the lines. And when I plug it in, I get true, false. And then I also have a value here, 3, 4, which is right there. And when I plug it in, I get false, true. So again, when I'm looking at systems, linear inequality systems, I'm looking for a point in a quadrant where I get true for all equations. And we can have more equations, and it's going to get a bit hairy here in a minute. Okay, so we're looking for true, true. In this case, because we have 2 equations, it has to meet all of them. You could also graph each inequality and then find the intersection. Okay, your calculator will do this, and you can easily look on Google or in the tutorial for how to graph inequalities with your TI-84 or how to find intersection. And you definitely want to find the intersection, because that's going to be a key part in some of the more involved analysis we're going to do in this chapter. Many problems in business, science, and economics involve finding the optimal value of a function. For instance, the maximum value of the profit function or the minimum value of the cost function, subject to various constraints such as transportation costs, environmental protection laws, availability of parts, and interest rates, etc. Linear programming deals with such situations. In linear programming, the function to be optimized is called the objective function. It is linear, and the constraints are given by linear inequalities. Okay? Linear programming problems that involve only two variables can be solved by the graphical method explained in example 1 that we already did. Okay? So when we only have two variables, we're going to use something called this linear programming using the graphical method about how to find that area. Okay, it's important to think about constraints. This is really common sense. Like, let's say you wanted to maximize the size of a room or the size of a fenced-in rectangle for your pets. Well, you might be limited to the constraint of your budget. So you have enough money, let's say you have $200 budgeted for this and you have to buy the materials. That's like a constraint. So like when you were thinking about cost, the cost has to be less than or equal to 200 because you have at most $200. Okay? And again, constraints are the ones given by linear inequalities. The objective function is a linear equation, and this is what we are trying to maximize or minimize, or we would use the word optimize. Find the maximum and minimum values of the objective function z equals 2x plus 5y subject to the following constraints. Okay, so our objective function is here because this is what z equals 2x plus 5y, because this is what we're trying to optimize, what we're trying to find the maximum and minimum values. These are our constraints, and we can tell that because they have less than or equal to all of them. Notice the last two says x is greater than or equal to 0 and y is greater than or equal to 0. This is telling us we're dealing in the first quadrant. This is very common when you think about it, because if you think about business things from a logical perspective or a common sense perspective, let's say that x represents the amount of hours I can work. Well, I can't work a negative number of hours, and maybe y represents the salary or something like that. I can't get paid a negative amount. So often the constraints on variables are that they are positive or 0. I can work 0 hours, or I can have 0 people working, etc. Okay, so that's very common, and all this is saying is we're really working in the first quadrant of the graph, and that the x and y axis are part of our boundaries. This is a vertical line or vertical inequality, so everything to the left or right, everything to the right of the y axis, and y is greater than or equal to 0 is everything above the x axis. So first we're going to graph what's called the feasible region of the system of inequalities. The feasible region is the intersection of all of these equations, and you can see why that's kind of like, whoa, that's a lot. It would be a wise decision to figure out how to use your TI-84 calculator to graph inequalities, because if you graph these all, and especially if you have a color model, if you don't have a color model, it's okay because it'll do patterns. You'll be able to see the area, the intersection area, okay? It'll use patterns, etc. when you look at the graph on your calculator. So what I would do is I would graph each of these. Remember how we did this, not the objective function, we hold that till the end, but I would graph each of these lines, 3x plus 2y equals 6. That's right here. And then I would graph negative 2x plus 4y equals 8. That's this blue line here. Then I would graph x plus y is equals 1. And that's this green line here. Now remember, x is greater than or equal to 0. That's the y-axis, and everything to the right, which is this line here, just this part here, intersects with it. And then y is greater than or equal to 0 is everything above the x-axis. So this line between 1 and 2 is part of that encloses the graph finally. Okay? So it's important that we can graph these linear inequalities and find the feasible region. The feasible region is this blue area. It's the intersection of all of these inequalities. Okay. Once we've done that, what we really care about are the corners of the feasible region. Optimal values, maximums and minimums occur at the corners or the intersections. Now this one isn't too difficult to figure out what the x and y coordinate is for each of them, because most of them, 4 out of 5 of them, are occurring on the axis. So I can see that this point here, this corner is 2, 0. I have another corner which is 1, 0. I have another corner which is 0, 1, and another corner which is 0, 2. The only one that's not quite clear what it is this point that is the intersection of two lines, negative 2x plus 4y equals 8, and 3x plus 2y equals 6. For this, I would use my calculator. If you go under the calc function, which is in the top row towards the right near graphing, if you hit calc function and then look at the menu there, you'll see an intersection button. And what you do then is it pulls up your graph and it'll say, are you on the first line? And so you want to be on either the blue line or the red line, because those are the one we're looking for this intersection. So we just want to be on this line. And once you've moved your little dot to this line, then you hit enter. And then it'll move to another line in here. And so hopefully it moves to the red there and says, are you on the second line? You hit yes, enter. It'll always ask if you want to guess, and just hit enter again, and then it will give you the actual coordinates of the intersection, x and y, for those two lines. Now what we do here, once we have all the coordinates of all the corners, is we build a table using this objective function, 2x plus 5y, and we simply plug in the points to this equation. For example, this first point here is 0, 1, x is 0, y is 1, into the equation 2 times 0 plus 5 times 1 equals 5. And so we're going to calculate all of those using a table. Okay, so we have 0, 1. That's our first corner. 2 times 0 plus 5 times 1 equals 5. Our next corner is 0, 2. Again, we plug it into the objective function. 2 times 0 plus 5 times 2 is 10. We go to the next one. This is the one we had to calculate with our calculator using the calc function and intersection. And the point is 1/2, 2 1/4. And we plug that in, we get 12.25. Then we go down to this point, which is 2, 0. We get 2 times 2 plus 5 times 0 equals 4. And we do the last one, which is 1, 0, or 2 times 1 plus 5 times 0. Okay? So we plug in the corner points, the x and y values, into our objective function, and we just calculate the values. In this problem, we're trying to find the maximum and minimum, okay? Once we've done this, we simply look at the numbers that we calculated. The largest number is the maximum. So our maximum value is 12.25, and it occurs when x equals 0.5 and y equals 2.25. Our minimum value is the smallest between all of these numbers, and that's 2. So we have a minimum value, or minimum objective value of 2 when x equals 1 and y equals 0. Okay? So again, when we're doing linear programming in two variables, we find the feasible area, which is the intersection of all of the inequalities. We then identify all of the corners by points, x and y. Once we've done that, we put the corner points into our objective function and just calculate a value. The largest value is the maximum. The smallest value is the minimum value. Okay? And this is called the corner point theorem. If a feasible region is bounded, then the objective function has both a maximum and a minimum value, and each occurs at one or more corner points. And we saw that before here. We saw the maximum value, which was here at this odd point, 1/2 and 2 1/4. And then I think we had a minimum value, which was either at 2, 0 or 1. I think it was at 1, 0, which was here. Okay. Now notice this is bounded. What that means is bounded is it's completely fenced in. You know, you would, if you were a rancher and these were cattle, you're good to go, because the cattle have nowhere to go because you've got fences around every single part. It's bounded on all sides. It's contained. Okay, but if it's possible that a region is not bounded, we call that it's unbounded. And you can see here with 2 lines, this feasible region just continues to go on and on and on. Okay, if the feasible region is unbounded, the objective function may not have a maximum or a minimum. But if a maximum or minimum value exists, it will occur at one or more of the corner points. So we're not really sure here. It's probably more likely, since this is continuing to go up, it's probably more likely that this graph would have a minimum, and there's only one corner point, so we'd only have one value to check. Okay? Notice here we have 2 equations, and it's unbounded. You have to have a minimum of 3 equations in order for a linear model to be bounded, right? We'd need at least one more equation to close in a section and make, in this case, a triangle, if you would. So again, the one on the left is bounded and the one on the right is unbounded. Sketch the feasible region for the following set of constraints. Three y minus 2x is greater than or equal to 0. Y minus 2x is less than or equal to 2. Y plus 8x is less than or equal to 52. And x is greater than or equal to 3. Then find the maximum and minimum values of the objective function z equals 5x plus 2y. So I want you to hit pause now and see if you can first graph this and find the feasible region, the intersection of all of these inequalities. Then find the corner points where they all intersect. Once you've done that, plug in the x and y values of the corner points into the objective function and see which is the largest, which will be the maximum, and which is the smallest, which will be the minimum. Okay, here's the graph. Hopefully you've paused for a minute. This one's going to be a little more complicated because, as you can see, all of the points are not on the axis points, etc. So you're going to get some good practice here in finding each of these intersections between y minus 2x equals 2 and y plus 8x equals 52, which will give you point D. X equals 3, this one's actually much easier because all you have to do is plug in 3 to the blue equation, y minus 2x equals 2, plug in 3 for x, and then calculate y. And down here, in this other equation, plug in x equals 3 into 3y minus 2x and calculate y. But we've got 4 different corners, so you need to figure out what those corner values are. And again, try this with your calculator using the calc and intersection functions on the top row to the right. Once you find the corner points, you're going to plug them in. And these are the 4 corner points. We plug them in, and we can see that the largest value is 49, and it occurs at the point 512. I guess that's up here. So we have a maximum of 49 at this point, and our minimum value is 19. It's the smallest value at this point. Okay. So let's try one more. Again, I want you to try to do this on your own and then look at it. That's the best way. I mean, I'm not doing a lot of the steps. I'm just kind of showing you a high level, and so it's really good idea for you to actually practice this on your own. Minimize. So we're only looking for the minimum here. We're only looking for the smallest value. Z equals x plus 2y. So this is our objective function, and we have 4 linear inequalities. X plus y is less than or equal to 10. 3x plus 2y is greater than or equal to 6. X is greater than or equal to 0, and y is greater than or equal to 0. So this is good because 2 of our equations are just the axes. So this is telling us we're in the first quadrant. Okay, when I graph those other 2 equations, I'm looking for the intersections. I have them here. If you're already looking at this, take a pause or rewind a little bit and try to find them on your own. I'm telling you, if you can't find them, it's going to be difficult on the test. Okay. Once I have those 4 points, I plug them in, and I'm just looking for the smallest, which is at the point 2, 0. Okay, and my minimum value of 2 occurs when x is 2 and y is 0. So this should get you going with linear programming using the graphical model. Do some great practice here because this is going to get a little more complicated as we move forward.